Welcome to The Explainer. Today, we're going to pull back the curtain on something you use every single second: electricity. But we're not just talking about light bulbs, we're talking about its hidden superpowers, these incredible forces that really shape our world. And it all kicks off in a pretty unexpected place.
So, picture this. You're walking around a school's science fair. You see this one project, a little crane, but instead of a hook, it's just got an iron nail with some wire wrapped around it. A student flips a switch and boom, this plain old nail suddenly picks up a whole bunch of steel paper clips. She flips the switch off and they all just drop. You look closer. There's no magnet anywhere, just a battery, a switch, and some wire. So what in the world is going on?
And that right there, that's the big question. It's the puzzle we're going to piece together. How does a simple wire, a nail, and a bit of electricity suddenly get the invisible power to lift solid steel? What's the secret?
To solve this, we need to uncover electricity's first hidden power, its secret ability to create a magnetic force. Now, this isn't some brand new discovery. No, it's something scientists actually stumbled upon more than 200 years ago.
Let's rewind the clock to 1820. A professor named Hans Christian Ørsted is giving a lecture. He's got an electrical circuit set up, and nearby there's just a regular compass. With the circuit off, no big deal. The compass just points north like it's supposed to. But then, the moment he flips that switch and current starts flowing through the wire, the compass needle goes wild. It jerks to the side and points directly at the wire.
And just like that, Ørsted had discovered what we now call the magnetic effect of electric current. It turns out, anytime electricity flows through a wire, it generates this invisible magnetic field all around it. It's not a fluke, it's a fundamental rule of physics. You stop the current, the magnetic field disappears. You start it up, it's back instantly.
The takeaway here is absolutely massive. It means electricity and magnetism aren't two separate things. They're two sides of the very same coin. Realizing this connection literally changed the world and opened the door to all sorts of new technology.
Okay, so if we know electricity can create a magnetic field, the next logical question is, can we control it? Can we build our own magnet that we can turn on and off whenever we want? Well, the answer is a huge yes, and it takes us right back to that science fair crane.
You know, think about a regular magnet, like one on your fridge. It's always on. You can't switch it off, and its strength is what it is. An electromagnet, on the other hand, is a magnet you're in charge of. Its power only kicks in when electricity is flowing. That means you can switch it on and off, and, this is key, you can even make it stronger or weaker.
So, back to that student at the science fair. How could she make her crane even more powerful? She's got two main options. First, she could increase the current, maybe by adding another battery to the circuit. More current means a stronger magnetic field. Simple as that. Second, she could wrap more turns of wire around that nail. Every single loop of wire adds to the magnetic field, concentrating its power.
And you might be thinking, cool science project, but this principle is the workhorse behind so much of our modern life. We're talking about those gigantic cranes and scrapyards that can lift entire cars. Those are just massive electromagnets. The old school bell at your school, an electromagnet. The motor that spins the fan in your room and even the loudspeakers that play your music, yep, all of them rely on this amazing, controllable magnetic force.
But wait, there's more. Magnetism isn't electricity's only trick. It's got another superpower, one that you probably use every single day, maybe without even realizing it: the power to create heat.
Let's think back to building that electromagnet. If you were actually holding the wires for a little while, you'd notice something else is going on. They start to get warm. And that's not a bug, it's a feature. It's electricity's second secret power showing itself.
This is what's known as the heating effect. You see, as electricity tries to flow through a wire, it doesn't just get a free pass. It runs into opposition, a kind of electrical friction that scientists call resistance. And all that struggle, all that friction, converts the electrical energy directly into heat. Now, some wires, like copper, have really low resistance. But other materials, like something called nichrome, have super high resistance, which makes them absolutely perfect for one thing: getting really, really hot on purpose.
And once you know to look for this, you see it everywhere. That cozy electric heater in your room, your hairdryer, the iron for your clothes, your electric kettle, they all work on this exact same idea: They're just simple circuits with a special high-resistance part inside that's designed to get hot and do a job for us. So we've got these two incredible effects, magnetism and heat, both powered by electric current. But in all these portable devices, like that little science fair crane, where does the electricity actually come from when it's not plugged into a wall? Well, the answer is a little hero we all know and love, the battery.
The story of the battery is just wild. It literally starts with a twitching frog's leg. Back in the late 1700s, a scientist named Luigi Galvani noticed that when he touched a frog's leg with two different metals, it twitched. He thought he discovered some kind of animal electricity. But another scientist, Alessandro Volta, thought, I'm not so sure. He had a different theory, that the electricity was coming from the two metals themselves, reacting through a liquid. So he swapped the frog leg for a piece of paper soaked in salt water, and he was right. In doing that, he created the world's very first battery.
Now, Volta's invention, this wet cell, was revolutionary, but it was also kind of messy, with all the liquid. The first big upgrade for portability was the dry cell. It uses a moist paste instead of a liquid, and that's basically your classic single-use AA or AAA battery. But the real game changer, the thing that powers our world today, has been the development of rechargeable batteries, especially the lithium-ion cells in all our gadgets.
I mean, the impact is just undeniable. Our phones, our laptops, our cameras, even our cars are now running on the magic of rechargeable batteries. They've untethered our entire lives from the wall socket. But there's a catch, isn't there? You've definitely noticed that after a year or two, your phone battery just doesn't seem to last as long as it used to.
And that brings us to our final question. As amazing as today's batteries are, they're clearly not perfect. So, what comes next? What's the future of trying to find that perfect portable power source?
Well, here's the challenge we're facing. The lithium-ion batteries that we all depend on need materials like lithium and cobalt, and there's only so much of that stuff on Earth. On top of that, they wear out. You can only charge them up so many times before they start losing their ability to hold that charge.
So let's dream for a second. What if we could solve those problems? What if you could have a battery that charged up completely in just a few minutes instead of a few hours? What if it lasted for years and years without really degrading? What if it was safer and didn't need such rare materials?
Well, that's not science fiction. That's the next big thing that scientists all over the world are racing to perfect: solid-state batteries. They get rid of the liquid or paste inside and use a solid material instead, which promises to make them safer, faster charging, and much, much longer lasting. To think we went from a twitching frog's leg to this, the journey of portable power is far from over. The race is on.